This is exponential functions, part 1. An exponential function is a nonlinear function of the form y equals a times b to the x power, where a is not 0, b is not 1, and b is greater than 0. In this type of problem, the independent variable, your x, changes by a constant amount, and the dependent variable, or y, is multiplied by a constant factor, which means that the consecutive y values form a constant ratio. And the graph of an exponential function will look like this. As my x values are going up, the y values are being multiplied by a constant factor. So they are getting progressively larger as we get larger x values here. In example 1, we're going to be identifying some functions. So if we look at this table in part A here, we notice that our x values are all increasing by 1 and the y values are increasing by 2. This means that our x values increase by 1 and our y values increase by 2, causing a constant rate of change, or a slope of 2. Therefore, this would be an example of a linear function. An exponential function would look like b, where we've got our x values going up by 1 and our y values are increasing by being multiplied by 2 each time. So as x increases by 1, y is multiplied by 2. That creates an exponential function. Let's evaluate some exponential functions. So in this case, we start with y equals -2 times 5 to the x power. And they want us to substitute for x 3. So my equation will become y equals -2 times 5 to the third power. So the first thing I'm going to do is my power. So 5 to the third power gives us 125. And then -2 times 125 is going to give us -250. Let's evaluate another one. This time it's y equals 3 times 0.5 to the x power, and they would like the x power to be -2. So y equals 3 times 0.5 to the -2nd power. Well, I'm going to rewrite 0.5 as the fraction 1/2 because I have this negative exponent. And in order to make my negative exponent positive, I want to do the reciprocal. So having 0.5 in fraction form, 1/2, is going to make it easier to find the reciprocal. It's going to be 2 to the 2nd power. Now I'm going to solve my exponent. So 3 times 4, which gives me the final answer here of 12. So I've evaluated these exponential functions. When graphing exponential functions, the form of our exponential function y equals a times b to the x power is a vertical stretch or shrink by a factor of the absolute value of a of the graph of our parent function y equals b to the x power. When a is less than 0, the graph is also reflected in the x-axis. The y-intercept of the graph is always a, the value of a. So let's see some graphs where we actually will see this in practice. So here we're being asked to graph f of x equals 4 times 2 to the x power. So the first thing I want to do is graph my parent function here in this case. So the parent function, which I'll call p of x, is going to be 2 to the x power. So if I start with 2 to the 0 power, 2 to the 0 power is going to be 1. 2 to the first power is going to be 2. 2 to the second power will be 4. 2 to the third power will be 8. 2 to the fourth power would be 16. Let's do a few in the negatives too. 2 to the negative first power would be 1/2. 2 to the negative second power would be 1/4. And it would be getting smaller, but never quite getting to 0. So there isn't 2 to any power that will get us to 0. So there's our parent function. So we're going to make a table of values for our f of x function. So I'm going to test -2, -1, 0, 1, and 2, and plug them into that function. So 2 to the negative second power was 1/4, times 4 would be 1. 2 to the negative first power was 1/2, times 4 would be 2. 2 to the 0 power is 1, 1 times 4 is 4. 2 to the first power is 2, 2 times 4 is 8. And 2 to the second power is 4, times 4 is 16. So let's graph these. So I have -2, 1, -1, 2, 0, 4, 1, 8, and 2, 16. All right, so let's compare these guys. If I look at the parent function and my f of x function, my copy here, I'll notice that the graph of f is a vertical stretch by a factor of 4. If I compare here at 0, I'm going from 1 to 4 as my y-intercept. So I'm stretching it by a factor of 4. When I'm looking at the domain for my f of x problem, the domain is going to be all real numbers. But the range is going to have some limits. In this case, our range is going to get close to, but never cross the 0 line. So the y values have to be greater than 0. Because they're all going to be above the x-axis. Let's take a look at one more example here. This time I have -1/2 to the x power. So first let's graph the parent function again so we can compare them. In this case, my parent function is going to, I'm going to call it p of x again. It's going to be 1/2 to the x power. So if I plug in some values here, 1/2 to the 0 power is 1. 1/2 to the first power is 1/2. 1/2 to the second power is 1/4. And if I do a few negatives here, 1/2 to the negative first power is going to be 2. 1/2 to the negative second power is going to be 4, and I can draw my graph right here. So it'll get close to, but never cross 0. So let's do the same thing. Let's make a table of values here for our f of x function. And let's test, once again, let's do -2, -1, 0, 1, 2. Stick with the same x values. So if I plug in -2 there, I'm going to have to do my reciprocal, so I'm going to get -4. If I do 1/2 to the negative first power, I'm going to get 2, and then it's going to be -2. 1/2 to the 0 power is 1, it'll be -1. Changing all these to negative because of that negative sign in front. 1/2 to the first power will be -1/2. 1/2 to the second power, it will be -1/4. Sorry about that. So let's graph these. So I have -2 to the -4th power, -1 to the -2nd, 0 to the -1st, 1 -1/2, 2 -1/4. And the graphs are actually a reflection over the x-axis. The only thing that changed between my parent function and my f of x here was that negative in front, which flipped my graph over the x-axis. So the domain of my f of x function is going to be all real numbers. And this time, since it's below the x-axis and will never quite get to 0, my range, my y values, are going to be less than 0.